Greetings. In this video, I'll be talking about the transform of a derivative and using Laplace transform to solve differential equations. Well, let's start with looking at what the Laplace transform of a derivative would be. Notationally, I could just write Laplace transform of f prime of t. Now I'm trying to find a Laplace transform of f prime of t, so fundamentally all I have is the definition if I don't know what that is. So I use the definition, e to the minus st f of t, but f of t here is f prime of t dt. So now here, if I conduct the integration by parts process, I'm going to let my u be e to the minus st. My dv will be f prime of t dt. My du will be minus s e to the minus st, and my v will be f of t. So the integration by parts would give me uv, which is e to the minus st f of t from 0 to infinity. Of course, don't forget the limits of integration, and remember this is an improper integral. And for the other one, you get minus the integral of v du. So minus plus the integral from 0 to infinity of v du, which is s e to the minus st f of t dt. So now if you look at the first one here, of course, remember, again, you notice the need for the function to be of exponential order, otherwise this term here would diverge. So here, basically, I have f of infinity, and I'm just going to notationally, there's no such thing as f of infinity, it's f of t as t goes to infinity, but without loss of generality, I could just loose hand it and just write f of t at infinity. I just write it as f of infinity. And exponential is in the denominator, so divide by e to the infinity, and then minus f of 0 divide by e to 0. So now f of infinity, e to the infinity grows much faster, so this whole thing goes to 0. So here I will get minus f of 0 plus, here s is a constant with the differential, so s comes out, and I have integral from 0 to infinity of e to the minus st f of t dt. And here you'll see I have minus f of 0 plus s, and if you recall, this is the very definition of Laplace transform of f of t, which is f of s. So therefore, that just simply becomes s Laplace transform of f of t, or I could also write it as f of 0 plus s f of s. And I've also seen it written as s f of s minus f of 0. Either way you write. So that is the Laplace transform of a derivative. So let's look at a couple of examples here. Let's look at the first example I wanted to do with you guys. It's y prime minus y. I'm taking a simple differential equation that you could easily solve. 2 cosine of 5t. And y of 0 equals 0. Now you notice to do the Laplace transform, we need initial conditions. And why do we need initial conditions? Well, because if you remember, few minutes ago, when we find the Laplace transform of a derivative, the answer is s f of s minus f of 0. So you need the value of the function in which you're finding the Laplace transform of, the value of the derivative function in which you're finding the Laplace transform of, to have its value defined at the initial condition 0. So if you didn't have f of 0, you couldn't have figured out the Laplace transform. So you must be given the initial condition. So it has to be an initial value problem. All right, so we have been given the initial condition. So let's start taking the Laplace transform. Now we know Laplace transform is a linear operator. So I could just take the Laplace transform of y prime minus Laplace transform of y. And of course, when I say y prime, you do know I'm talking about y prime of t. Or if I say y, I'm talking about y of t. Okay, so equals to 2 Laplace transform of cosine of 5t. So now let's take the Laplace transform using the definition. Laplace transform of y prime is s y of s minus y of 0 minus Laplace transform of y is just y of s equals 2 times, now Laplace transform of cosine of 5t is s over s squared plus 25. And I'm sure you all remember that. So now y of 0 is 0, and that's always nice for the initial conditions to be 0, so it doesn't add to the complexity of the algebraic expression you're going to have to work with. And notice here that if I factor out the y of s, I'll end up with s minus 1. And on this end, I'll end up with 2s over s squared plus 25. Now I am ultimately solving for y of s. So from here, I have y of s equals 2s over s minus 1, s squared plus 25. So now this is my, oops, sorry guys. So this is my solution to my differential equation, but it's in frequency domain. So this is basically like the algebraic version of the solution. And if I want to try to attempt to put it in a box one more time, and I'm successful this time. Okay, so that's my solution in frequency domain. Now, my differential equation initially was in time domain, so obviously I'm looking for y of t, not y of s. So I want to find y of t. So basically at this point, all I have to do to find my solution in time domain would be to take the Laplace inverse of y of s. So y of t, which is my solution to my differential equation in time domain, will simply be the Laplace inverse of y of s, which is the Laplace inverse of 2s over s minus 1 s squared plus 25. And now you see why we had to practice finding Laplace inverse of different functions, so that when you're solving a differential equation, you notice you're always going to end up with a Laplace inverse problem to work with. So that's why we had to practice working with Laplace inverse transforms. Now here, as you recall, we need to do a partial fraction decomposition, and I am not going to waste this video to do that. So I'm going to assume that you could do that yourself or use Mathematica to do it. Either way, I don't care. So I have y of t, which is my solution in time domain, is the Laplace inverse of this expression. And if I break this apart, it will be the Laplace inverse of, okay, and I've done partial fraction decomposition here, so it'll be 1/13 1 over s, let me see which one I wrote first, s minus 1, right, minus 1/13 1 over s squared plus 25. And that's right, and then ultimately I get plus 5/13 1 over s squared plus 25. So I'll let you write that down. So 1/13 times 1 over s minus 1 minus 1/13 times s over s squared plus 25, and plus 5/13 actually, sorry, good thing I read this again. That should be a 5, because you're going to end up with 25, and then you have to break it into 5 and 5 so you can make that a perfect sign. All right, so that's what you end up with when you do partial fraction decomposition. You decompose the fraction above. So this is simply now y of t is equal to Laplace inverse of, well, actually, you know what, let's just pull out the 113 because we all know Laplace inverse is a linear operator. So Laplace inverse of 1 over s minus 1 minus 1/13 Laplace inverse of 1 over s squared plus 25. Is that right? Am I having everything right? That's right, and that has to be in. And guys, that has to be an S. Good thing I caught that. Okay, great. So I knew I needed an S here. Very good. So so far so good. Plus 5/13 Laplace inverse of 5 over s squared plus 25. That's right. So when you do the Laplace inverse, just to make sure we're together at this point, you get a 1 here, you get an s there, and you get a 25 here where you break it into 5 and 5 so that you could then, you know that then that's going to be a known Laplace inverse. Now I've broken it all apart, so now my solution y of t is going to be 1/13 e to the minus e to the t minus 1/13, and that's cosine of 5t, plus 5/13, and that's sine of 5t. So that becomes my solution in time domain. Put it in the box. So there's my solution in time domain. All right, so let's look at one more exercise. We'll look at the following differential equation. Y double prime minus 3y prime plus 2y equals e to the minus 4t. Now I have to have initial conditions, so y of 0 is equal to 1 and y prime of 0 is equal to 5. Well, now this is not really desired because, as I said earlier, we always like for these initial conditions to be equal to 0 so that we'll end up with a simpler expression to work with, but it is what it is. So let's start with taking the Laplace transform of this differential equations. So again, I'll write it formally. Laplace transform of y double prime minus 3 Laplace transform of y prime plus 2 Laplace transform of y equals Laplace transform of e to the minus 4t. Now Laplace transform of y double prime is s squared y of s minus sy of 0 minus y prime of 0 minus 3. Now Laplace transform of y prime is sy of s minus y of 0 plus 2 Laplace transform of y is just y of s, and the Laplace transform of e to the minus 4t is 1 over s plus 4. Now let's replace y of 0 with 1 and y prime of 0 with 5. So I have s squared y of s minus s times y of 0, which is 1, minus y prime of 0, which is 5, minus 3s y of s plus 3y of 0, which is 1, plus 2y of s equals 1 over s plus 4. Okay, so let's combine like terms here. So I'm going to take all the y of s's and put them together. So let's see, y of s, I'll end up with s squared. So that one's gone. Then the next one is negative 3s. So now this is gone. And then the next one is plus 2. So now this is gone. Okay, now then the next terms are minus s. And I have a 5 plus minus 5 plus 3, which is minus 2. So now these three expressions are gone. So I'm pretty cleaned up with the left-hand side, and the right-hand side would simply be 1 over s plus 4. Now if I rewrite this and clean this up a bit, this is s minus 1, s minus 2, y of s equals s plus 4, 1, plus s plus 2. Now I can actually write that a little higher, plus s plus 2, because obviously I'm going to have to find a common denominator here. So I'm at least going to skip that. So I'm going to have you just complete that. So I'm just going to write what we're going to get. So I'm going to have s minus 1, s minus 2 times y of s. And that gives me, if I find a common denominator, that will give me, write that down. Okay, so that will give me s squared plus 6s plus 9. And in the denominator, it will give me an s plus 4. And then I'll divide both sides by the coefficients of y of s. So then this becomes s minus 1, s minus 2, s plus 4. And I'm dividing at this point both sides by the coefficients. So both of these are gone at this point. So my final y of s will be s squared plus 6s plus 9 over s minus 1, s minus 2, and s plus 4. So now this is my solution to my differential equation, but it's my solution, as you know, in frequency domain. And my given differential equation was in time domain. So therefore, I want my solution to be y of t. And I know y of t is simply Laplace transform, Laplace inverse of y of s, which is basically Laplace inverse of then my expression here, s squared plus 6s plus 9 over s minus 1, s minus 2, and s plus 4. Alright, so if I do again use Mathematica or just algebra to do the partial fraction decomposition here, I'll end up with y of t is equal to 25 over 6 Laplace inverse of 1 over s minus 2 minus 16 over 5 Laplace inverse of 1 over s minus 1 and plus 1/30th Laplace inverse of 1 over s plus 4. Now you're wondering why I wrote s minus 2 first, whereas here I'd written s minus 1. First of all, that's a multiplication and it's commutative. Doesn't matter how I write it, but since the coefficient of s minus 2 was positive, I started with that. I didn't want to start my solution with a minus. I don't know. Call it superstition. I don't know. So that doesn't really matter. So now I could easily find my solution by looking at these Laplace inverses and remembering exactly what each one is. So my solution will be 25/6 e to the 2t minus 16/5 e to the t plus 1/30th e to the minus 4t. And that will be my solution of the given differential equation in time domain. Well, have fun doing these problems, guys. So this will do it for our session on solving, deriving the formula, deriving the Laplace transform of a derivative and creating a formula for that, and also practicing the use of Laplace transform in solving differential equations. Thank you and see you next time.